person is moving, but why? Why to move? This is a good question. Why to move? You can see here in the video, the person wants to grasp butter, for example, in the refrigerator. The person is going in front of the refrigerator, opens the door, but the problem is the butter is not accessible. And the motion here have no sense. Why to move? Because the goal is not reachable. And we have worked on this problem, the problem of accessibility of objects in environment for persons with disabilities. I have time enough? Okay. We have worked with a specific context. First, an environment, indoor environment, only indoor environment. And the person can move, but either with a wheelchair, sit on the wheelchair, or with a trolley, in each person, for example. And each person has not the same disabilities. And we must adapt the system according to the limits, the articular limits of the person. And we want to assess, to evaluate the environment accessibility, but in a reasonable computing time. All points on the environment. But the precision is not very important. 1 or 2 centimeter precision is enough. Our approach here to verify the accessibility depends on the configuration of the environment, 3D environment, the bulk of the person with this motion device, a trolley or wheelchair, and we must have a model, mathematical model of the human articulated structure. And the approach to verify the accessibility is to find, to verify if the solution exists for reaching a set or all points in the environment. Our test bed is here a kitchen, but I'm sorry, it's not blue in reality, but there's a problem with the technical problem. Here there is a kitchen, and we want to verify which point is accessible and which is not accessible. Yes, and the bulk, the surface the person uses on the floor. If the person on the left here have a trolley, then we can consider that the bulk, the surface on the floor is circular. On the right, the person sits on a wheelchair. And here we consider that the bulk is rectangular. It's not the same approach to solve the problem if the surface is rectangular or circular. We must have a mathematical representation of the articulated structure of the person. Here I represent articulated structure coming from the waist to the fingertip of 21 degrees of freedom. This is robotics. 21 degrees of freedom. Only the person without the motion device. And the problem is to find if there is a solution such that the joint structure of a person can reach a given point in the environment. This is a problem. And then, if we find a solution, we must generalize to all points in the environment. But we need to control this joint structure to find the solution, if the solution exists. There is 3 main solutions to apply to this problem. First, to adapt an analytic method. there exists an analytic method, the INGL, for example, to solve the inverse kinematics problem, but only for 7 degrees of freedom. If we decompose the system, the 21 degrees of freedom, it's possible to have a solution. The second possibility is a linearization of the problem and to apply the pseudo-inverse method to find the inverse kinematic. And the third solution is optimization method, for example, to apply genetic algorithm, but it's quite long computing time, or gradient descent, like BFGS or Newton-Raphson, for example, methodology, but there is every time drawbacks, for example, local minimum. Our approach is to use an algorithm, very simple algorithm, to modify each articulation one to the other, and to verify after modification if we approaching the goal. If yes, we keep the value. If not, we don't keep the value. And this is very simple and very fast. But we need to model, to have a direct modeling in order to compute the difference between the actual position the real position we want to reach and the actual position of the articulated structure. This is the first equation, and we need to compute f of theta, which is a direct model of the 21 degrees of freedom system. Here we use the Danoit-Artenberg formulation, good known from robotic researchers. I want not to go into detail. Some result. We have applied this to 10,000 tests on a PC, classical desk PC, with a precision of about 0.5 unit. There is centimeter here, 0.5 centimeter. We have an execution time for one computing time of about 6 milliseconds. But the solution we find depends on the initialization of the variable. But it's not very important because we want only to know if a solution exists, that the person must adapt his possibilities. And this is only the computing of the articulated system. There is the person without the motion device. And we must adapt the motion device to this algorithm. What we know that in black here, we have the polygon which represent the area the person can move, the limit of the area. And in blue, you have the model of the person. And we add to the model 1 degree of freedom, and 1 degree of freedom in rotation, and 2 other degrees of freedom, x and y, that modelize the motion of the device system. And the degree of freedom on rotation is adapted to the basic structure, and the 2 other degrees of freedom, there are translation, are put on the, I want to show you. This is a point we want to reach. And on this point, we modify the goal point in order to take into account the evolution area in black. And here, the point we want to reach is not the objective point, but is all this polygon. And this, if we adapt this if we adapt this, if we consider, this time I have finished. If we consider a circular and a rectangular shape, we must modify the evolution area. For example, a rectangular shape is a bit complicated. We must modify the evolution area according to the orientation of the wheelchair. And the evolution area we put on the goal point, it depends on the orientation of the wheelchair. Here, because the point we want to reach is not more one point, but a surface. And there are more points on the surface. And the execution time is more faster. We have an execution time of about 3 milliseconds. I have two... I finished. I'm sorry, it's turning in blue, but you can see on the video... No, you don't see the result. Yes, there is a green point and blue point, but in reality it's red. If the point is green, we are sure the point is accessible. If it is blue, the point is not accessible. For example, the tap here is accessible, the window is not accessible, the box is not accessible. For one person on a wheelchair, here the person is on a wheelchair, with able parts, upper part. The shelves are not accessible, for example. The second one. On the second one, the person is on a wheelchair, but the spine is rigid. And you can see here, the bottle and the glass are accessible, green, accessible, but the shelves are not accessible. The microwave oven is not accessible here. Before it was accessible. It is not accessible because of the configuration of the kitchen at this point. Okay, I have to conclude now. I have to conclude, but I know there is no conclusion. Because robotics is a very open technology, and I think it's a real challenge for different applications of the future. But we must take in mind the second point that assistive technology, and robots in particular, should help the user, but not to perform the task in his place. This is very important in the application of robotic and all assistive technology to people with disability. Thank you for your attention. I think if you have some question, I will try to answer to it. Thank you.
Si en la sala hay algo...
Would anyone like to ask a question? If so, please raise your hand and a roving mic will come to you.
Interesting speaking. Thank you very much. Muchas gracias a todos.